Good morning, everybody. So, today we are going to talk about types of radiation, how we balance nuclear equations, and identifying which type of radioactive process is being represented in an equation. So, first, what is radiation? Radiation can come in the form of particles or waves, and it is basically either waves or particles that come off of a substance like a radioactive material, or from a radioactive process like fusion or fission that can come in contact with other types of matter and create either beneficial effects or harmful effects. Okay, so some of the radioactive particles that you need to make sure that you guys are aware about are alpha particles. Alpha particles are exactly the same as a helium nucleus. And so, therefore, the symbol that we use for alpha is 4 over 2 He. So, this right here, this is an alpha particle. So, when you see this symbol in a nuclear equation, this is the same thing as an alpha particle. And you've got to make sure that you link that in your brain. Another way that you might see this written is this symbol is also alpha. So, you could see a 4 over 2 alpha like this. Same thing. Okay, another type of symbol you need to be aware of are called beta particles. Beta particles are the same thing as an electron. They are negatively charged and they also can be emitted from a radioactive isotope. Beta particle symbol is right here. So beta particles. Same thing as an electron. So remember, the mass is on top here, which is the 0, and the -1 is the charge. You might also see it written like this, 0 over -1 with a capital B like this with a tail. That is a beta symbol. That is the same thing as a beta particle. So either one of these, if you see those in an equation, that is a beta particle. Okay, we've already talked about neutrons. Neutrons look like this. They have a symbol of an N, and the mass is 1 and the charge is 0. Okay, so this is the symbol for a neutron. They can also be emitted from radioactive isotopes and or decay processes, or fission reactions and or fusion reactions. So neutrons are also a particle that can be considered radiation. It may not be considered quite as harmful because it doesn't have a charge. Alpha particles are positive, they're positively charged, and beta particles are negatively charged. Neutrons are neutral, obviously no charge. Okay, so that means usually without a charge, they're a little bit less harmful. Positrons are essentially positive electrons. I don't know what happened there, sorry. Positrons are positive electrons. So the symbol for a positron will be 0 over +1b or a 0 over +1e. Okay, so those are positrons, positive electrons, which I know seems kind of odd, but it is a possible form of radiation that can also be emitted from radioactive isotopes. Okay, so erase this, and then we will go to the next slide. Okay, so next slide. Oh, just kidding. There we go. Next slide. Okay, so here's another version, another screen that shows the different types of particles. One that I want to point out on here that we have not yet talked about is the gamma ray. Gamma radiation is represented like this symbol right here that kind of looks like this. This is a gamma symbol. I also want to point out that the gamma radiation does not have mass or a charge. It has neither. So it is 0 over 0. So if you see gamma radiation in an equation, it does not affect the mass or the charge or the atomic number of the substance that it's being emitted from. Okay, we'll talk about the importance of that later in this presentation. Okay, so now, radiation as waves. So radiation can be particles, but it can also be considered waves. So the electromagnetic spectrum is the diagram or the chart that we use to describe all of the radiation that we experience that comes from waves. Okay, So some of these waves are harmful to us and some of them are not. So you can see on here on this chart that we have everything from radio waves here, which have a really long wavelength and a very low frequency, all the way up to gamma rays, which have a very short wavelength, really, really short, and a very high frequency. Okay, so what this means is if you have a really short wavelength and a high frequency, that means that it's usually more penetrating. So gamma rays are able to go through more materials than radio waves. Radio waves are not, they're long and they're not basically as powerful because we're going to learn, especially in the next unit, that the wavelength and frequency of electromagnetic waves depends on the energy involved. So these also have super high energy. And that means that when they do go through things, they can be a little bit more harmful than radio waves. Okay, so this is a spectrum. So you've got radio waves, then you've got microwaves down here, which we are all familiar with. Infrared rays, sometimes the red light that comes out of your remote is infrared. Then we have the visible spectrum here. Okay, so this is the spectrum that we can see, and it's not very big compared to the entire spectrum. Ultraviolet is beyond violet, which is right here, which is why it's called ultraviolet. And that is the type of radiation that we get from tanning or the sun. Okay, and then X-rays are next. So you can see once you get past the visible spectrum over here, I don't know why it keeps doing that. Once it gets past the visible spectrum on this side right here, this is what we call ionizing radiation. Ionizing radiation has enough energy and enough high power that when it hits other materials, it can cause it to create ions. So ionizing radiation is usually more harmful to us than non-ionizing radiation, which is usually in the lower range down here. Okay. So this leads us to the discussion of, well, how penetrating are these types of radiation? What stops each of these types of radiation? Alpha particles are the largest. Okay, so a helium nucleus, these are really large. They're very big. So it does not take much. You can stop alpha particles with paper. It won't go through your skin or your body. So if alpha particles are on the outside of your body, you're pretty safe. The reason that alpha particles can become dangerous is if they get inside your body, which will never be an accident. So if you ingest alpha particles, it was some sort of intentional. Okay, that also kind of goes back to Radium Girls and how they were actually ingesting the alpha particles. They just didn't know that they were. And so once alpha particles get inside your body, they're super dangerous because they can't get out, right? They can't go through skin. Beta rays, beta particles, okay? They can go through paper, they can go through your skin, okay? But they will be stopped by things like thin aluminum foil, okay, or thin foils. So aluminum foil, that kind of thing, thin pieces of copper or lead or that kind of material will stop beta radiation. Then you have gamma rays and X-rays. They're pretty close to each other. They go through our body. We know this. That's why they're able to illuminate our bones. They also go through thin pieces of foil. They are stopped by thicker things like lead. The reason lead is because lead is super dense. Okay, it's way more dense than most other metals. So it is able to stop that type of radiation. Now, there's also neutron rays or neutrons. Neutrons can go through pretty much everything. They even can go through lead. They are stopped by water or concrete, which is part of the reason that you will learn that they use water in a lot of nuclear facilities. Okay, and that's part of the reason is they're able to stop neutrons from traveling. All right, so next, we're going to talk about how we balance nuclear equations. Now, we talked about this a little bit and we looked at fusion reactions in class. But I want to remind you that when you are balancing equations, the mass, which is the top number, it keeps doing that, the mass, which is the top number, must be equal on both sides of the equation, okay? Which means the arrow. So your arrow is your equal sign on top and on the bottom, okay? And the mass has to be equal, which is on the top. And then the charge and atomic number, which is on the bottom, also has to be equal. So I treat these like two separate equations. And I say we've got 238 equals 0 plus x, because this is what we're trying to find out. Well, I know that If I subtract 0 from 238, I still have 238. So that is my x in this case. Then I'm going to do the exact same thing on the bottom. I have 93 equals -1 plus x. This is the reason I like to write this out. When you're dealing with negatives, it gets confusing. To take this to the other side of the equation, you're going to add 1 on both sides. So then what happens to your isotope is it becomes a 94. And then you're going to look on the periodic table because remember, this is your atomic number. So you are going to look on the periodic table and see what element 94 is, and it is plutonium. So we're going to write Pu. So that is where the symbol comes from. You have to use the atomic number and the periodic table to get your element symbol. Keeps doing that every time I go back and forth. Okay. All right. So next, now what we want to look at, next example. In this case, we have two things on the left and two things on the right. If they are on the same side of the equation, you have to add them together. So in this case, I'll go ahead and erase a little bit here. Okay. Oh, perfect. Okay. So in this case, my equal sign is going to be here and here. And I'm going to take 253. I'm going to bring up the plus sign, and 4 equals 1 plus x. So if it's on the same side of my equals, I'm going to add it together. So essentially I have 257 equals 1 plus x. Well, then if I subtract 1 and subtract 1, I have 256 on top over here. Okay, down here I've got 99 plus 2 equals 0 plus x. So on this side, if I add those together, I get 101. Then once again, I'm going to look for 101 on my periodic table, and that is going to give me my element symbol of Md. All right, we've got one more example. So on the bottom here, we have 142 plus x equals 142. So I know immediately that this is a 0. Then on the bottom, I'm going to move over here. I've got 61 plus x equals 60. Well, if I subtract 61 from both sides, my x is -1. And I learned that anytime I have a -1 on the bottom, that means that it is either an electron or a beta particle, which are the same thing. So I'm going to use beta here. You could also say 0 over -1 electron. They're both correct. Okay, so that is how you balance equations. Pretty easy. So next, now what you need to know is there are 4 major types of nuclear reactions, and you have to be able to identify them. So first and foremost is fusion. So we can tell that this is a fusion reaction because we start with 2 isotopes that are fairly small, and we end up with a bigger isotope, right? Now, this one is a little bit trickier. Sometimes you will see 2 smaller things. If you are generating a larger thing and then something that is still small, okay, the reason this is small is because it's a 1, that is okay. Sometimes you will also generate a neutron in the process, okay? If you generate a neutron, that's fine also. That doesn't mean that it's not fusion, okay? So now let's look at this example. So during one type of nuclear fusion, an atom of helium-3, so I'm going to write down helium-3. So helium-3 is my mass. Now, when I look on the periodic table, I see that my atomic number for helium is a 2. So if it's not given to you, you need to look for the atomic number. It is going to react with, so that's a plus, an atom of helium-4. So helium with a 4 to produce, and that's still a 2 because it's helium. To produce, that's where your arrow comes in. To produce an atom of beryllium-7. So 7 goes on top, beryllium goes on the bottom. Now, or goes as your symbol. Now, to find out what is on the bottom, I need to look at my periodic table. And since it is a 4, that kind of matches. That means that I do not have any other particle. I do not have any other particle here, right? Because this matches. 2 plus 2 is 4, and 4 plus 3 is 7. Okay, so I want you to make sure that you can recognize and write out equations for fusion reactions. Okay, next type of reaction is called a fission reaction. We haven't talked about these a lot yet, but you guys are going to be learning about these this week. So the way that you balance it is the same thing. One thing that I want to point out here, though, that can happen is you sometimes have a coefficient. If you have a coefficient in your equation, that means that you must multiply by the number on the top and the number on the bottom before you add your stuff together. Okay. So in this case, I know that I have a blank here, but I also know that it already tells me that it's 37. So I can go ahead and look on the periodic table and see that 37 is rubidium. So Rb. Now, this one I do not know yet. This one over here, I do not know yet. So I have to balance to figure that out. Okay. So I'm still going to do my equation. So I've got 1 plus 235 equals 2 plus 90 plus 144. Okay, so when I add those together, that's 146 and 90, 236 and 236. Perfect. Okay, and since this one is already over here, I didn't really have to do that. Okay, now this one we do not know, so we do have to do the bottom. So we have 0 plus 92 equals 2 times 0, which is 0, plus 37 plus x, because we do not know this. So that means that I will take 92 minus 37 to figure out what my x is. Okay, keeps doing that. So that is a 5, and that is a 5. Okay, so this is a 55. So I'm going to look on my periodic table for 55, and I see that it is cesium. So that is how we finish that reaction. Now, a couple things I want to point out about fission reactions. You will see that you're going to start with a very, very large nucleus. Sometimes it's going to be initiated or started. The reaction will be started by a small particle like a neutron. Okay, so those are going to be the reactants that you look for to be able to tell that it's fission. Then, oftentimes you will get some neutrons coming off, and you will get 2 isotopes here that are usually different, that are much smaller than your original isotope. Okay, so see how these are much smaller? Okay, and when I say much smaller, they're going to be pretty close to each other. Okay, so you don't want just a neutron in one of these things, because then that is not a fission reaction. Your large nucleus needs to split almost in half. Okay, so that is how you know that it is fission. Now we're going to look at this equation down here. So this one is kind of strange because it's having you split your fission reaction into 2 steps. The first step is you're going to add these together to get this product. So you're going to get a 236 here and a 92 here, and it's still uranium, okay, because my atomic number didn't change. Now on this one, we want to know what particle is over here. So now I'm going to kind of ignore this part, and I'm going to treat this like my equation. So I have 236 equals, because that's where my arrow is, 141 plus 92 plus x. And then on the bottom, I have 92 equals 55 plus 37 plus x. Okay, so I'm going to add these together on this side first. So 233. So this is 233. So when I subtract, I get my x over here should be a 3. And then on the bottom, when I add these together, my x actually should be a 0, because this is 92. So if I subtract 92 from both sides, my x is going to be a 0. Now, I do not know of anything that is a 3 over 0. However, if I have a 0 on the bottom, I know that's a neutron. So what this probably means is I have 3 neutrons. So if you have a 0 on the bottom, it has to be a neutron. And I know that a neutron is 1 over 0. So if I have a 3 on top, remember that's the mass. So if I put the 3 in front, when I multiply, I get the same answer. Okay, so I have 3 neutrons here. I know that one's a little tricky. Okay, now I'm going to let you work on this one on your own, and you're more than welcome to ask me. I want you to practice writing it out, and then you can ask me to verify your answer. Okay, if it's got 2 neutrons here, remember you're going to put the 2 in front and the 1 over 0 in. Okay, so those are fission reactions. Now, for an alpha decay reaction, this is where, so when you have decay reactions, so decay reactions, what that means is you have 1 reactant particle only. So see here how I only have one reactant, and see here how I only have one reactant. I don't have two particles ever. So that is how you know it's a decay reaction. Okay, well, how do I know that it's an alpha reaction, Ms. Watson? You were looking for your products. So if it is an alpha decay, one product, so this is alpha, because one product is going to be an alpha particle. Okay, so in this case, this one's already done for you. It's already balanced. And since I see an alpha particle right here, I know that this is an alpha decay. It's a decay reaction because I have one reactant, and it's an alpha decay because one of my products is an alpha particle. Okay, now I'm going to look at this one down here. So I have uranium-92, and it's going to thorium-228. I've got to figure out what's missing. So 232 equals 228 plus X. So when I subtract, I get a 4 on top. And then down here, I have 92 equals 90 plus X. So on the bottom, I have a 2. When I look on my periodic table, I see that 2 is helium. And then because of my infinite wisdom, I remember that a helium nucleus as a product means this is an alpha decay. Okay, so that's how I solve, and then that's how I recognize what type of reaction it is. Next one is thorium. You're going to start with thorium-234. To figure this out, you look at your periodic table. So I'm going to go to thorium, which is 90. Then I know it's a decay or an emission. Decay and emission, same thing. Decay and emission, same thing. So that means that when I see that, I know that that is my only reactant. That is my only reactant. And so I know that I'm going to have an alpha particle as one of my products. So that means this is going to be 4 over 2 He. And then I can figure out what is missing. Okay. So when I do this, my top then, I've got come on, pen, 234 equals 4 plus X. So this should be 230. And then on the bottom, I have 90 equals 2 plus X. So this should be an 88, right? And so when I look for 88 on the periodic table, I see that this is radium. Okay, so that is how you would do that whole process. Last one we're going to talk about is beta decay. So beta decay, same kind of idea as alpha decay. If it is a decay reaction, once again, you will have one reactant, which means before the arrow. And you're going to have, since it's beta, you will have one of your products will be a beta particle. Okay, so that is how you know it's a beta decay reaction. So in this case, I can see real easy, if this is 144 and this is 144, this has to be a 0. And if this is 58 and this is 59 plus X, if I subtract 59 from both sides, my X is -1. Well, when I have a 0 over -1, that is beta, or you can write it as 0 over -1 electron. Both of these are beta particles, either one. And so this is a beta decay reaction. Okay, now this problem down here is the same thing, but it's in words. It tells me that I start with iron, which is Fe59, and I have to look on my periodic table to see that iron is 26. It decays by beta emission. So that means if it decays, that means that this is my only reactant, and beta is one of my particles, so 0 over -1b. And then I got to figure out what's missing. So if I have 59 equals 0 plus X, this is going to be 59. And this is 26 equals -1 plus X. So remember, I have to add 1 to each side. So this is going to be a 27. And when I find that on the periodic table, I see that that is cobalt. Okay, so that is how you complete a beta decay reaction in words.